So one of John Hughes's principles of functional programming is to use whole values. Whole values. But what does that mean? Hi, my name is Eric Normand, and these are my thoughts on functional programming. So whole values it's kind of a subtle idea, but it's something that I think needs to be shored up and kind of made more definite, because he doesn't ever explain it in definite terms anywhere. He just suggests we use whole values and gives some interesting examples of it. And so I would like to try to define it, but I don't know if I'm ready. So I'm just going to explore the idea a little bit and see where it goes. Now, the thing is, I do believe that he's right, that this is an important thing in functional programming. It really helps. So I do believe in it. I use it myself, and it really feels right. But that doesn't mean I could put what I'm doing into words. So that's what I'm trying to do right now. Okay, so let's imagine that we have some imperative algorithm, and this algorithm requires us to keep track of two different numbers, and so we make two variables and we update each as they need to be updated. For instance, if you wanted to calculate the average of a list of numbers, you could initialize two variables to 0. One of them is called the sum and one of them is called the count. And you iterate through the list, and every time you see a number, you add it to the sum, and store it back in sum. And then you add 1 to the count and store it back in count. Right? And so then at the end, you divide them out and you have figured out the answer. So at each stage of the loop, each iteration through the loop, you got these two numbers. You got the sum and the count. But they're separate. There's no indication in your program that they go together, and they definitely do. As you know, I've talked about calculating an average using the ratio, so that instead of storing the numbers separately, you put them into a tuple where you have a sum and a count in the tuple. And that's an example of keeping the values together and making them whole. Because separately, they're not meaningful, but as a whole, they are. And so this lets you pass it around like an argument, and you can have a much more coherent set of operations on them, because you have both values all the time. Now this is actually, when I've been reading about Smalltalk, again, I bring up Smalltalk for some reason, but I think a lot of this stuff was known by the Smalltalk group, the original group. In Smalltalk, the whole purpose of objects is to bundle two values together that need to be in a relationship, so that you can transactionally modify them to maintain that relationship. And so that's all we're talking about, is bundling values together into a composite value that those two values are kept in a relationship. It might be 3, whatever. Okay, so let's come up with another example. I was doing some coding yesterday, and it was a recursive descent parser. And one of the things that I needed was two values coming out of so when I parsed, let's say I parsed a number out of this stream of characters, I needed two things: the number that I parsed, and then the rest of the stream. Like where did I get to when I finished parsing the numbers? And so I bundled those up as a tuple. And if you extrapolate that to sort of the whole architecture of the entire parser, not just parsing integers, but parsing everything, you start to see that this bundling is very useful, to be able to say, here's the value that I've got, and here's the rest of the stream at all times. Because then you could be adding to that adding to that value. So like, let's say you're parsing a list, so you have to parse one item at a time, add it to the list. You're maintaining the entire state of the parser in one single value. And so instead of kind of ad hoc passing these things around as arguments, and sometimes you need one and sometimes you need the other, you just always bundle them together. And it just makes for a much cleaner interface to everything. I would like to give one more example. This is the example that John Hughes gave, which is he was talking about a system that someone came up with to draw graphics. And this was quite an old example. But the example was that it was a system where an image was represented as a function, and the arguments to that function were the axes on which you're supposed to draw that picture. So you would skew it to fit in the axes. So you could have it where they're orthogonal, the two axes, and wherever the point is where they meet, well, that's the bottom left corner. But then if you were to sorry, you're backwards to what I'm seeing. If you were to skew them like this or move it, it would move the image to another spot and would like squish it. Okay, so that's interesting, but really what it's saying is that function was complete as a whole value. It could be drawn anywhere on the screen, contained everything it needed to draw, and the thing that was variable were the arguments, like where it's going to be drawn and what the axes look like. And so it was a complete unit. It could be completely opaque because its interface was very clear. It could be composed in very known ways. And that's the example that he gave. And I think that's another interesting example. It's this idea of the whole value. So instead of having an image that was, say, like an array of pixels, and then an algorithm, like a function or something else that would, I guess a function that would take the image and the two axes and make a new image that would then skew it, and then take this skewed image, and you could then draw that to the screen. it was done in a much more elegant way that allowed for interesting patterns, because you could pass in the axes and then to a function, and it would change the axes, pass them to to the image, and then it kind of recursively do it, so you have this like fractal effect. You know, it's much more interesting to do cool stuff with. It's much easier to do that kind of functional recursive stuff when you're dealing with it at that level. I don't know about how beautiful these images were, by the way, but I do find that kind of thing helps, where you have the whole value. Yeah, I don't know about any other examples, but I'm going to try to define it now. And the real essence of it is that you take two or more values, usually it's a small number of things, and you put them into a composite value. So that could be a tuple, or you could define a new type. You put them into this composite value, and the composite value represents a semantic whole that you can then define new operations on top of. Okay, this is very much like, when I say it like this, it just sounds so much like object-oriented programming, right? Where you are grouping state together and putting an interface on it. But that's not what I see most people doing with object-oriented programming. Usually what they're doing is they're not thinking in terms of the relationships between the data and how to make operations to maintain those relationships. They're thinking more like, what's all the data we can put in here? Let's group it together and call it a person, right? Or let's group it together and call it a inventory manager. I don't know what they would call it. And then what are those operations that we need to do on it, right? We need to read it, we need to write it, and we need, they're not doing this much more relationship-based analysis. So here's the tip. If you're doing object-oriented programming, you should look into doing it like this, where you're thinking about, like, instead of doing this for loop and maintaining two different variables, those two variables should be bundled together. Does it make sense to bundle them together? Because once you've bundled them together, it could be that the operations, now this is me thinking functionally again, the operations on them have interesting properties. Like if they're associative, that means you can do much more free recursion on them. If they are commutative, it means you can distribute your algorithm, not worry about what order things come back in, and you're going to want to bundle those values together anyway, right? Maybe if it's associative, you can find an identity value, you've got a monoid. Okay, so there's things that you can do with them once they're bundled together. You can start to analyze the properties of those operations that maintain the relationship. It's actually another property he talks about, principle he talks about. He talks about combining forms. That's what he calls them. We call them operations. But he's talking about, you take two of these whole values and you combine them in some way. So if it's an average, you're taking the two averages, you add them up, you have another average, right? Take two of these images that take the same, skewed axes, and you can overlay them, right? Or you can put them side by side or something like that. It's a combining form. All right, I'm about to get on the greenway here. A lot of bikes. It's like a highway for bikes. So I'm trying to define this. This idea of whole values. Okay, I want to talk, before I define it, I did want to talk a little bit about this talk I saw by Fred George. Fred George is I guess he's a product manager now, or project manager, something like that. He's an old timer, very experienced programmer. I started getting into him because he talked about what his management style, which is called developer anarchy or something like that. And the idea is just give the programmers some KPIs, some goals to hit, and let them hit it. Let them go and figure out ways to increase those metrics. And don't give them user stories and stuff like that. Let them come up with them on their own. And there's a whole, it required a whole architecture, like a microservices architecture, so that they could work independently and things like that, without breaking the entire system. But he also had another talk called The Secrets of Agile Programming or something like that. Secret Practices of Agile Programming. And it was trying to say that when a lot of the Agile practices were invented, a lot of them came from extreme programming. And it was assuming that you were programming basically like Kent Beck. Like, do all these practices, do pair programming, do continuous deployment, do test-driven development, all these things that we kind of think of as agile style things, modern software development practices. They also assume that your programming style, your coding style, was in a certain way. And so he described a few of these things. And one of the things he said was your classes should have 2 or at most 3 fields. Right? And so, the audience was like, what? That's not possible. And he's like, look, go analyze your classes and the fields that they have. And I'll bet that you'll see that some of those fields have a stronger relationship to each other than they do to the others. Right? So if you have a person class, you'll see that, hey, this street name goes together with the zip code much more than it goes together with their salary, right? And maybe those should start to be grouped together to represent that relationship. That the whole point of this is to start representing the semantic information in ways that your programming language supports. And if you're just throwing them together like a big bag, you're not going to be able to move as fast, to program as quickly, because you're just going to have these big bag objects that just kind of do everything. And the secret is to break them out into smaller objects that have much more coherence between the fields. And I think that's very much related to this functional programming idea of whole values. Don't have a bunch of values that have a relationship and that they're split apart. Like they're split into even something as simple as the two arguments to a function. Put them together. You'll notice that composite might have certain properties. There's also the idea in a whole value that you could have partial solutions to problems. So instead of saying, well, we either have the solution or we don't, you might have a partial solution. And it's sort of like this parser example that I gave, where you have some value and then the rest of the problem, right? The rest of the problem is being stored, or is part of the answer. Hey, I parsed 4 characters for you. Here's the number that represents. And here's the rest of the stream. This is all the characters that weren't part of that number. And you put them together and it makes sense together. Okay, I'm going kind of long now. And I just want to say thanks for listening. It really helps me to get my ideas out, walking and talking and sharing them with people. And I love it that you